All right, guys, welcome to 4.3 rotations. This is advanced geometry. If you're not in advanced geometry, then you're wasting your time watching the rotations video. So I would watch a different video if you're not in advanced geometry. So on this video, we're going to talk about rotation. So this is going to be the third type of transformation that we've seen. We've seen translations and we've seen reflections. Those are the first two. Now we're going to see rotation. So a couple notes really early on, not too hard of stuff. Go ahead and pause your video. When you pause your video, all I really want you guys to do is to just look at this stuff up here, okay? Just this stuff up here would be important for you guys to have, okay? So that's the only things you need are, I lost my mouse, there it is. Only stuff you need is up there. So go ahead and write that down. That would be great. And then we're gonna go from there, okay? So pause your video, write down this top sentence. You don't need this picture, you don't need this right here, that's fine. Just write the first part up here, okay? So pause your video and come back. All right, so hopefully you are back and you wrote down this top part. A couple important features up here. It just says a rotation is a transformation, we talked about that, in which a figure is turned about a fixed point. This is going to be important, we'll talk about that in a minute, called the center of rotation. Rays drawn from the center of rotation to a point in this image form the angle of rotation. Really, the bottom line is this, is that you're going to have the center of rotation. Now, all the problems that we're going to do, that center of rotation is going to be the origin. We're not going to be doing some random points. There's some stuff that we could possibly do later on, but right now this is what we're looking at, okay? So we have this point. We're going to rotate things around the point. Angles are only going to be 90, 180, 270. You'll see that here in a little bit, okay? So what we're going to do is we're going to take an object like this right here, and we're going to rotate the whole thing. That's the goal, okay? So we're going to take an object. We can maybe take like a triangle and we take it, we rotate it around a fixed point. That fixed point is going to be the origin on every problem we do. If we had more time and we were in person, we could use stuff, then we could do it this way, but we don't. So I'm not even going to bother it because it's kind of a pain in the butt if we're not doing it. Okay, so I'm going to jump to my next slide. Once it comes up, all right. I want you to pause your video and I want you guys to write everything down up here. Make sure I'm not hiding anything. So go ahead and pause and do that. All right, guys, welcome back. Once again, I want you guys to write everything down up here. Hopefully you guys did that because this is the big, most important part of this, what you want to get out of this right here, okay? And really, it's going to be these three things that are the big keys, okay? So what these are look like, and these are all rotated counterclockwise about the origin. The origin is right there, counterclockwise, going this direction. So what's going to happen, and it doesn't all your point doesn't always have to be in the first quadrant. This example right here shows it in the first quadrant of what's happening. So when you rotate something 90 degrees, what happens is that you flip the B and the A around, and the B becomes negative. When you reflect it 180, you take the opposite signs. 270, flip A and B around, take the opposite of A. Have these close. When you guys do your homework, if you have these close, your homework will be simple. If you don't have these close, then you're going to have to keep going back and look at it. Or if you just try to use your head, it's going to be a little bit harder for you guys to do that. Okay, so make sure you guys have this written down. This is like the big key of what we're going to be doing. We're going to jump to an example here next. So give me a second. Let me erase my board and we'll go on to example number 1. So example number 1, what we're going to do is that I'm going to tell you to graph, triangle ABC. I kind of get this good way. Click my button, my bad. Click the graph ABC with vertices here, 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 and its image after 180 degree rotation about the origin. They didn't tell us which direction, which is fine. If they don't tell us which direction, assume that we're going counterclockwise, okay? So what we're going to do right here, we are reflecting at 180. So if you recall, what happens then is of our stuff, we're going to be taking opposite of A and opposite of B. So what I'm going to do here is I'm going to, before I graph them, I'm going to list all my new points with the prime. So A, what I'm going to do is take the opposite of each value, -3 and -1. That's how that looks like. When I do B, I take the opposite of each one of those, -3, -4. C, I'm going to take the opposite of those two, -1, -1. This one was pretty easy, primarily because these were all positives, so we had to flip it. Now, what does the picture look like? This is what the picture looks like, besides my mug up here. You started off with this, the rotation. It took it 180 degrees. Each of these points went 180 degrees, and we did that by flipping those signs that we just did. Okay, so that's what we have. That's how we do a rotation. That's what we're going to be looking at. Knowing these rules right here on that last page is the key. Okay, I'm going to erase, and we'll move on to the next example or next problem. Boom. So the next part, and this is going to be a brand new. So this has been talked about, not so much by me, but in the other sections. And this little key part right here, which is called rigid motion. And the only reason I want to bring this up is that this may appear on a test, not my test, but like an SAT, ACT, that you may want to look at. So what is rigid motion? That's my next question. Rigid motion is where an object transforms but does not change shape or size. Okay, so if you change something and it moves, then it doesn't change the shape or size, then it's what we call rigid motion. Back in the day, we used to call that an isometry. You don't necessarily need to know the word isometry. You need to understand rigid motion. That's how they start talking about things now in 2020 and so forth. So all this means, and all the transformations we've done so far, translation, reflection, and rotations, have all had rigid motion, which means it just doesn't change size and shape. We can move it left, right. We can rotate it. We can reflect it. It still does not change the size or the shape. And that's what rigid motion is. And that's what an isometry is, if you need to know that. Okay. Not going to be on my test, but you may need to know that language. Hopefully you'll remember it. 50-50 chance. I bet most of you guys are pretty smart. You probably will if you guys watch the video. Okay. All right. So next one, example number 2. So what's going to happen on these examples is we're going to do a combination of changes. So what's happening here is that we're just going to take this little point, this little segment. Okay. So it says graph RS. So all R and S are is just going to be a segment, just something like that. Okay, with one endpoint, another endpoint. And what we're going to do is we're going to do a composition of transformations. The first one, we're going to rotate it 180 degrees. And then what we get from there, we're going to reflect it. Okay, so how does that look? Well, what you're going to see here is the first part, when I take R and I want to rotate it 180 degrees, I change the signs. So it becomes -1, -3. Then what I do is I then need to reflect it in the y-axis. So you need to go back to your notes in 4.2 and recognize is that when we reflect something, we change the sign of the x for the y. Okay, so here is what we got first. This is the rotation. So you take your original point, rotate it 180 degrees. Then you reflect that point to be here. Now, if you notice, I'm doing each of these points separately. Honestly, I think it's probably the easiest way to do it is if you look at the points. If you notice, I haven't shown you the graph yet. I think it's harder looking at the graph. I like looking at the points, recognizing what my rules are. You know, we know this rule right here is -a, comma, -b. Okay. And then this rule down here is going to be -x, comma, y. So the only thing that changes is whatever the x value, x sign is, okay? So if we jump to the next one, I take 2 comma -6, but I change the signs and I get -2 comma +6. Then if I want to reflect it over the y-axis, the only thing I should change should be the y, and it does. It goes from negative to positive. So these are my points, and I want to look at my graph. That's what we're looking at, okay? So my graph shows the original picture down here. Oh, son of a gun. Hold on 1 second. I gotta wait for my little guy to come up here. All right, never mind. Anyway, so what's happening on that picture is everything gets pushed away. So it goes around, and that's what reflection and then the translation does, okay? If you need more examples, I'd be more than happy to do that. Sorry about that. Didn't mean for that to go away. All right. So last little bit of notes, and then we have one more example after this. Rotational symmetry. This is brand new. So rotational symmetry. So it's kind of like we talked about line symmetry the other day, where you could draw a line through something. Rotational symmetry is very similar. It's when the figure can be mapped onto itself by a rotation of 180 degrees or less. So if it's more than 180, so it's 360, that doesn't really count. It's got to be 180 degrees or less, about the center of the figure. That center is always going to be the origin or a point on there. So I have a little picture right here, and you're going to see a couple examples. Most examples I give you are probably going to be something like this. Now, here's 0 degrees, here how it starts. So if you rotated something 45 degrees and it gave you the exact same thing, that's how it worked. So on this one, if you notice, this has a rotation of 90. It also has a rotation of 180. Whatever goes back to the original picture. 45 degrees is not giving me the original picture. 90 degrees is 180. One of the things you can recognize when you start talking about rotational symmetry is if it has 4 equal parts like that, if it has 3 equal parts, if it has 5 equal parts, that's what's really going to kind of stand off for rotational symmetry. That's what you want to look at. Okay, so let me erase right here. Boom, 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 boom. Example number 3, it says, does a figure have rotational symmetry? So I'm going to give you 3 pictures. Here's the first one, okay? So I'm going to go ahead, I'm going to put my marker on here. It says, does a figure have rotational symmetry? So can you take this and turn it where it's going to be exactly the same? Recognize this, this, and this. These 3 things are going to be the most important parts. So what happens here, if you took this triangle and you rotate it, because it's an equilateral triangle, this doesn't work for every triangle, but because it's an equilateral triangle, if you rotated this there, it would also be there. So how do I know what angle that's going to be? Well, we know that we have 3 sides, right? We know that each angle is 60, 60, 60. You could take, actually, you could look at whatever the exterior angle is. If you guys remember, son of a gun, I meant to have this up here. Sorry, don't go to that example yet. Just look at this example. So what's happened here, this angle is 120. And I know that because we have a center of the circle. And when you rotate this, if you want to rotate it back on there, you take 360 divided by 3, which is the number of equal sides and equal angles, and that's going to give you 120 degrees. So this means, and anytime you have what we call a standard figure, which means that all sides are the same, you can divide like this. That means that this is a yes, and it has a 120 degree rotational symmetry. Okay, so really one of the keys is that you have to look for things that are exactly the same as you go. Okay, so this is the second one. If you notice, no sides, no angles are the same. This is going to be a no symmetry because you can't take that and rotate it without going 360 where it's going to be the exact same. So once again, look for things like this, the equal angular and equilateral. That's going to be helpful. And then our last example looks a little bit weird, okay? Now, if you notice, see how opposite sides are the same of both of these? This is going to be a yes, and the rotational symmetry it has is going to be 180 degrees. So if you have like opposite sides like that are congruent, that's going to be a little bit easier. And if you look at this, to turn that thing, you would turn 180 degrees and to give you the exact same picture. So many things is just going to be all about look. That's what you're going to have to do as you go through this. Okay. So that's all I have for you guys. So this is all the notes we have. Hopefully they went well. If you have any questions, please send me an email or hang out. I'd be more than happy to go over anything that you guys like. And we'll go with that. Okay. So you guys have a great afternoon. I miss you, and we will talk to you guys on Tuesday.